Hello and welcome to all students. In this lecture, we learn about absolute and conditional convergence of a series. Absolute and conditional convergence of an infinite series. So, in the previous lecture, we studied about geometric series, convergence and divergence of a series. After that, we studied a algebra of convergent series, test of convergence, alternating series, and in this lecture today we are going to study about absolute convergence. In the next lecture we will study about the ratio test and the root test. So first of all we see what is meant by absolute convergence, or first of all we see what is absolute series of a given series. If we are given any series, say summation n runs from 1 to infinity, we have another series summation mod n equal to 1 to infinity, and this series is given by mod a1 plus mod a2 plus mod a3 plus dot 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 plus mod an plus dot dot dot, whose terms are the absolute values of the original series, whose terms are the absolute values of the original series. So for any given series we can write its absolute series. So let us define what is meant by absolute convergence of a series. A series summation an is said to be absolutely convergent or converges absolutely if the corresponding series of absolute value summation mod n equal to 1 to infinity is convergent. Okay, see the definition once again. A series summation an is said to be absolutely convergent or converges absolutely if the corresponding series of absolute values series mod an is convergent. Means a given series summation an is said to be convergent if its absolute series is convergent. In this case we say that given series summation an is absolutely convergent. Okay, so let us take one example. Consider the series 1 minus 1 half plus 1 by 4 minus 1 by 8 plus dot dot dot. The given series is summation minus 1 raised to the power n plus 1 n equal to 1 to infinity 1 upon 2 raised to n minus 1. Means the given series we have written in the summation notation summation minus 1 raised to the power n plus 1 into 1 upon 2 raised to the power n minus 1. Okay, so this is the compact form of this given series. Now I want to write its absolute series. Just we have to remove the negative signs and we have to place the positive signs only, and then we will get the absolute series of the given series. So nth term of given series is minus 1 raised to the power n plus 1 1 upon 2 raised to n minus 1, and it is for all n runs from 1 to infinity, for all n belongs to n, capital N. Therefore absolute mod an is equal to 1 upon 2 raised to the power n minus 1. Therefore summation n equal to 1 to infinity summation mod n runs from 1 to infinity. This is absolute series of a given series, and it is equal to summation n equal to 1 to infinity 1 upon 2 raised to the power n minus 1. But if we observe that this is a geometric series, this is a geometric series with common ratio 1 half, and common ratio r is equal to 1 half. We will see here. Now the series on the right hand side is a geometric series with mod r is equal to 1 half, means common ratio, and that common ratio is strictly less than 1. Therefore, by the theorem on the geometric series, we can say that the series summation mod n runs from 1 to infinity is convergent or converges. Thus, the series is absolutely convergent. See here. The given series is absolutely convergent because its mod series is convergent, or we can say because its absolute series is convergent. Therefore, given series is absolutely convergent. Now, let's take next example. Example number 2. Consider the series 1 minus 1 half plus 1 by 3 minus 1 by 4 plus dot dot dot. Series is not absolutely convergent because its mod series, because the corresponding series of absolute values, that is 1 minus 1 half plus 1 by 3 plus 1 by 4 plus dot dot dot, being a harmonic series and it does not converge. Therefore, the given series is not absolutely convergent. So in this example, the given series is given and its absolute series is not convergent. That's why given series is not absolutely convergent. So now we study about the conditional convergence of a series. So first of all, we write the definition of conditional convergence. A series summation an is said to be conditionally convergent. A series summation an is said to be conditionally convergent if it is convergent but not absolutely convergent. See here. A series summation an is said to be conditionally convergent if it is convergent but it is not absolutely convergent. That is, if summation an, series summation an converges but summation mod an does not converge. So when we say that given series is conditionally convergent, when that series itself is convergent but its absolute series is not convergent, means it is divergent. So in this case we say that the series is conditionally convergent. Let us take one example. The alternating harmonic series हे काय काम आहे तुमचं? होय, सेकंड सेमिस्टरची काय? मग एक अर्धा तास थांबता का जरा, माझं लेक्चर सुरू आहे. लेक्चर झाल्यानंतर तुम्हाला सांगतो मी काय करायचं ते. चालेल ना? अर्धा तास लागेल मला. काय 11:30ची गाडी आहे इथं, आता लेक्चर सोडून येऊ काय मग? हां, the alternating harmonic series, a series summation an is said to be conditionally convergent if it is convergent but not absolutely convergent. If summation an converges but summation an does not converge. Example 1. So what is conditionally convergent series? A series is said to be conditionally convergent if that series itself is convergent, but its absolute series is divergent. In this case, we say that the given series is conditionally convergent. The alternating harmonic series. For example, the alternating harmonic series 1 minus 1 half plus 1 by 3 minus 1 by 4 plus dot 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 is convergent, but its absolute series 1 plus 1 half plus 1 by 3 plus 1 by 4 being a harmonic series is divergent. See here, the given series is 1 minus 1 half plus 1 by 3 minus 1 by 4 plus dot dot dot, and its absolute series is just put all the positive signs. So 1 plus 1 half plus 1 by 3 plus 1 by 4 plus dot dot dot, and that absolute series is a harmonic series and that series is divergent. Okay, and therefore the alternating harmonic series is conditionally convergent. Okay, the given series is convergent and its modulus series is divergent. In this case we say that the given series is conditionally convergent. Okay, so let us take one theorem based on this type of convergence. Theorem says that if a series summation n runs from 1 to infinity is absolutely convergent, then it is convergent. Once again, if a series summation n equal to 1 to infinity is absolutely convergent, then it is convergent. So this theorem says that if series is absolutely convergent, then that series is convergent. Okay, so let us we try to prove this theorem. Write the proof. Note that the inequality an plus mod an is always greater or equal to 0 and it is always less than or equal to 2 mod an. That inequality is true and it is true for all n, for all natural numbers. Okay, for any real number it is true, is always true, as a modulus of an is either minus an or plus an. Since the series summation n runs from 1 to infinity is absolutely convergent, and this is given to you, the series summation an is absolutely convergent. This is given to us. We know that series mod an is convergent. As given series is convergent, therefore as given series is absolutely convergent, therefore absolute series of given series is convergent. Therefore mod an is a convergent series. Okay, thus summation 2 times mod an is also convergent. So multiplication by a non-zero scalar does not affect on the convergence and divergence of a given series. Therefore series 2 mod an is also convergent. Hence by comparison test we get that series an plus mod an and runs from 1 to infinity is convergent. So here we have used the first inequality which we have stated here in the second line. So by the comparison test, the given series summation an plus mod an and runs from 1 to infinity is convergent. Okay, so this is now convergent series. Now what we will do here is we write summation an like this. Summation an is equal to summation an plus mod an minus summation mod an is a difference of two convergent series. So as we have seen, summation an plus mod an is convergent and summation mod an is also convergent. So it is the difference of two convergent series, and we know that from the algebra of series the difference of two convergent series is also convergent. Therefore series n runs from 1 to infinity is also convergent. Okay, thus by algebra of convergent series, the given we get that series an and runs from 1 to infinity is convergent. Let us take one example. Example 1. Discuss the absolute convergence of this series. So first of all we see what is the series. So 1 minus 1 by 4 plus 1 by 9 minus 1 by 16 plus dot dot dot. What we have to do here, we have to discuss the absolute convergence. Okay, So just we have to check the modulus of that series. Okay, absolute series of a given series, whether it is convergent or whether it is divergent. Okay, so let us write the solution. Given series is 1 minus 1 by 4 plus 1 by 9 minus 1 upon 16 plus dot dot dot, and that series we can write in compact form, means in summation notation. Summation minus 1 raised to the power n plus 1, n runs from 1 to infinity. Summation minus 1 raised to the power n plus 1 into 1 upon n square, n is equal to 1 to infinity. The corresponding series of absolute values is given by 1 plus 1 by 4 plus 1 by 9 plus 1 upon 16 plus dot dot dot. And this series in the compact form we can write in this fashion. Summation 1 upon n square, n runs from 1 to infinity. So if I put n is equal to 1, 2, 3, 4, we will get all the terms of that absolute series. So this is a absolute series, and we observe that this series is a p series with p is equal to 2 and it is greater than 1. So we know the conclusion, which is a p series with p is equal to 2 still greater than 1, and hence it is convergent. That is very simple. Therefore the absolute series is convergent. Therefore the absolute series of a given series is convergent. Therefore the given series is absolutely convergent. Given series is absolutely convergent. Hence the series is absolutely convergent. Thus we further conclude that the original series is also convergent. We further conclude that the original series is also converges. So original series is convergent. Yes, absolutely convergent series is also convergent. That's why the original series is also convergent. Okay, let us take next example. Example number 2. Discuss the convergence of the series summation sine n upon n square, n equal to 1 to infinity. Here the corresponding series of absolute values is series sine n upon n square, n runs from 1 to infinity. Here the corresponding series of absolute values is series mod sine n upon n square, n runs from 1 to infinity, and it is equal to series. So n square is always positive, so it is not necessary to write mod for n square. We write modulus for only sine function. So summation n equal to 1 to infinity mod of sine n upon n square, and we write all the terms of this series. It is equal to mod sine 1 upon 1 square plus mod sine 2 upon 2 square plus mod sine 3 upon 3 square plus dot dot dot. We compare this series with series 1 upon n square, n equal to 1 to infinity. We observe that mod of sine n is always less equal to 1 for every n, and therefore we can say that mod of sine n upon n square is less than or equal to 1 upon n square for all n. So 1 upon n square is the dominating series, and it is also a p series, and it is convergent series. Therefore the given series means, therefore the absolute series is convergent. That is my conclusion. So see here what is thing now. The series summation 1 upon n square, n equal to 1 to infinity, is converges being a p series with p equal to 2, and it is greater than 1. Therefore this dominating series summation 1 upon n square is convergent, and therefore thus the original series converges absolutely, and hence by the theorem the original series also convergent. The original series is also convergent. So that was very simple example. Now let us write some remark. If p is a positive constant, then the sequence 1 upon n raised to p is a decreasing sequence with limit 0. Yes, correct. It is a decreasing sequence and converges to 0. Thus the alternating series summation minus 1 raised to the power n plus 1 1 upon n raised to p, this series is also convergent. Okay, is always convergent. If p is greater than 1, the series converges absolutely, and if p lies between if p is strictly greater than 0 and less than or equal to 1, then the series converges conditionally. Okay, so this is the end of our lecture, and we stop here, and thank you very much.